Hi everyone. In the previous lectures, we discussed about series and parallel LC circuits. So now I thought I'll generalize the results and present it in a more formal manner. So the first, here in this lecture, we'll mainly discuss about second order lossless transfer functions. Now what do I mean by that is that the poles, the system will actually contain two poles on the j omega axis, a maximum of two poles, in fact only two poles on the j omega axis. So such systems, I'm just calling it here as second order lossless systems. Okay, so there are four possible transfer functions for such systems. So we'll be discussing all those four transfer functions in this lecture, and we'll see how will the system behave for an impulse and step inputs. And here the results we'll be deriving will be very generic of nature. So any other circuit which we'll be analyzing in the future lectures, you can always correlate the responses that we get in this lecture. So first I'll start with a low pass second order lossless system. So the DC gain of this system is h of 0, and it's a resonant system, purely lossless resonant system. So it has an infinite gain at omega equal to omega naught. So if I want to plot its frequency response, so then I'll have to substitute s equal to j omega, and we would get 1 minus omega by omega naught the whole square. So if you are to plot the frequency response at omega equal to 0, it is h of 0. Okay. Now at omega equal to omega naught, this function becomes infinity. So the function would first increase like this to infinity, and then it would roll off eventually. So you need to know what is the slope with which it's going to roll off. If let's say I'm plotting it on a log scale, then we need to know what is the slope with which it is going to roll off. So at high frequencies, when omega much greater than omega naught, this function will reduce to minus h of 0 into omega naught upon omega the whole square. So now if you see here, this function is going to roll off as a second order low pass function, so wherein after the pole, like second order low pass function rolls off as two integrators. So omega naught by omega square, I tell you the slope of this, if I take 20 log of the magnitude and plot it, so if I take 20 log of h of omega, I'm going to call this whole thing as h of omega, and plot it, the slope of this will be minus 40 dB per decade. Okay, and the phase response will be quite interesting for this, is that now for any value of omega less than omega naught, any value of omega less than omega naught, this term h of 0 by, it's a real, if you notice this, h of 0 by 1 minus omega by omega naught is actually a real function. It's not a complex number, it's a real number. Now for any value of omega less than omega naught, this term will be less than 1. So this term overall will be greater than 0. So the phase will always be 0 degrees. Now the instant omega goes greater than omega naught, at that point you would have this term greater than 1. So therefore the denominator will be negative, so the whole term will be less than 0. So at that point the phase will be negative, so it will be by 180 degrees. So it will go from 0 till minus 180 degrees and stay there. Okay, for any frequency greater than omega, so there will be a sudden discontinuity in phase at omega equal to omega naught. In fact, all the filters that we have discovered, we have encountered in the previous lectures, they all had a gradual, graceful transition in phase. They went from, for a single pole system, it could go from 0 to minus 90. Okay, for a system with a 0, right, or left of plane 0, it would go from 0 to plus 90. The shift will always be graceful, it will linearly increase, but here, or it will increase in a tangential, the function was an inverse tangent function. But here, if you see here, it was actually a sudden change. It's actually a sudden change in the phase at omega equal to omega naught. Okay. Now we'll try to find the impulse and step response for this system. So I have a system which is of this form. It's a simple second order lossless low pass transfer function. Now if I feed an impulse, if I want to find the impulse response, I will use Laplace transform. The impulse the Laplace transform of delta of t is 1. So using that, I'd simply write it as omega naught h of 0 by omega naught square plus s square plus omega naught square. This here is h of 0 omega naught into sine omega naught t into u of t. So that's the impulse response for this function. So if I feed delta of t to this system, okay, the output is going to be this. I'm going to call it h of t. The impulse response as this. Okay, it's a sinusoid. You can see that the impulse response is a sinusoid. Again, we already tried to analyze this in the previous lectures. We said if this system has a pole at s equal to omega naught, so therefore if I feed an impulse which has constant energy at all frequencies, the frequency omega naught is going to see an infinite gain. So therefore you are going to get a finite power output, and we discussed this in the last lecture. So that's why you're getting a sinusoid as an output here. Okay, so since it's a low pass system, you can't have a t equal to 0 when you're applying an impulse. It's a sudden change. Your output will not have a sudden change. It will start from, it's going to be a sinusoid. You might wonder why not cos omega naught t. I mean, there, if the output is a cos omega naught, then there is a sudden change in the output. Okay, but this is sine, because sine starts from 0 and then it reaches a peak value and comes back. Okay, so that's the whole discussion here. So the omega, the output frequency will be a sinusoid. It's not cosine, it's a sine, and that should also make intuitive sense here. Okay, again, as I said, there are different ways of looking at this function itself. So for example, if you look at this function h of 0 by 1 plus s by omega naught square, for very high frequencies, when omega much greater than omega naught, I can approximate the transfer function as h of 0 into, I can ignore 1, so the s by omega naught square will dominate. It will become omega naught by s square approximately. Okay, I'm just going to ignore the term, s is j omega anyways, I'm just going to ignore the term 1. Okay, so because of that, you will get a transfer function of this form, h of 0 into omega naught by s square. So this is nothing but a second order integrator. There are two integrations. So if I take an impulse function and integrate it once, you will get a step function. If I integrate it twice, this is omega naught square, sorry. So if I integrate it twice, you should get a ramp function. So at t equal to 0, this is what I'm just analyzing this at the instant you applied the input. So that's at t equal to 0. When you apply an impulse, it's going to behave like a second order integrator, and the gain of the integrator will be h of 0 into omega naught square. So you should actually get, if I apply say unit impulse, you are supposed to get h of 0 omega naught square into t into u of t. After two integrations, this is what you should get. And if I look at the time domain response, which we actually obtained a few moments ago, is if I substitute for small values of t, for very small values of t, I can approximate sin x as x, or sin omega naught t as omega naught t, and you would get this as h of 0 into omega naught square t into u of t. So that's how you get that response. Okay, fine. And so this is the response for an impulse function. Now I'll feed a step function, which is u of t, to this system, h of 0 by 1 plus s upon omega naught square. Now for this, again, I'm going to use the Laplace transform. So u of t, the input, when I feed the unit step function, the Laplace transform is 1 by s. When I feed it to this system, you'd get a function of this type. Okay, so I'll just use again partial fractions. So to expand it, you'd get so I'll write it as s by omega naught square. Okay, so if I multiply these two terms, I'll be left with I'd get the function back. And this function, if I now compute the inverse Laplace transform for this, 1 by s, it is u of t, and this function is nothing but s by s square plus omega naught square, which is cos omega naught t into u of t. So the overall step response for the system will actually be h of 0 into u of t, or h of 0 into 1 minus cos omega naught t into u of t. So that's the step response for the system. So if you try to plot the step response for the system, okay, if you try and plot the step response for the system, you would actually have, you will start at t equal to 0, it starts at 0. Again, as we discussed, it's a low pass system, so it has to start at 0. Okay, and you would actually have the value here. If you notice this function is always positive, and this function is always positive, so you're going to get an output like this. I'm just plotting the time domain, the response of the system as a function of time, and the average value of this function is going to be h of 0. And that should make sense, because when you feed a unit step function, so the input function that you fed to the system is this. Okay, I have shown it. This is u of t. I'm assuming here h of 0 is greater than 1. It can be even less than 1. So this is u of t. So when you applied u of t, you are getting, ideally the steady state value is nothing but when I multiply u of t into h of 0, that's the steady state value. Okay, because it's a DC gain of the system is h of 0, and it's a step input, so steady state it should reach a value of u of t into h of 0. But since it's a pure lossless system, there will also be an oscillatory component on top of it. The average value will be h of 0 into u of t at t tending to infinity, but there will always be a sinusoid riding on top of it. Okay, and again we will see why does this come. I mean, we already discussed it. There will be some form of energy that is getting stored either in the capacitor or inductor, and that will keep going back and forth between the inductor and capacitor for eternity, in a lossless system. If there was a resistor, then it would have decayed down, but this system is a pure lossless system, so it will forever persist. Okay, so that's all about the simple low pass second order system. So next system is the high pass system. Okay, so first we'll try to draw the frequency response of this system for very low frequencies. For S, that is omega much less than omega naught, this function will be 0. So I can ignore this term. So it will behave like S upon omega naught the whole square into h infinity. So this is nothing but a second order differentiator. They're just putting two differentiators in cascade. Okay, we already discussed a differentiator Laplace transform is d by dt. The Laplace transform is S. So this is like a second order differentiator. And at very high frequencies, S by omega naught would become much greater than 1, and I can ignore 1, and you will get a transfer function of h infinity. So this is for omega less than omega naught, and omega much greater than omega naught, you will simply get a constant value of h infinity. So that's why we call it as a high pass filter. Okay, and again for omega equal to 0, the gain is 0. At omega equal to infinity, the gain is h infinity. You can very easily verify that. So I'll draw the frequency response. So this is omega by omega naught with a minus sign, 1 minus omega by omega naught the whole square. So this function for omega, so this function at omega equal to 0, I said it's going to rise with the slope. I'm going to plot this response as on a logarithmic scale. So this will be mod of h of omega, and h of omega is the transfer function here. Okay. Now for low frequencies, this function, I said that we can ignore this term, and it will reduce to h infinity into omega by omega naught the whole square. This is, I'm plotting only the magnitude, it is actually minus of this. So this is going to rise with a slope of 40 dB per decade, 40 decibels per decade, and at omega equal to omega naught, it's going to reach infinity. Okay. Now for omega much greater than omega naught, this function is eventually going to reach a value, a finite value, which is h of infinity. Okay, so this is 20 log of h infinity. Okay, so this is the transfer function, frequency response for a high pass system, a lossless second order high pass system. And if you want to plot the phase response for omega, for small values of omega, the phase is actually minus 180 degrees. Okay, now as frequency increases, when as you increase the frequency for omega greater than omega naught, so this term will become greater than 1 and the denominator will become negative, so the overall phases would cancel out and the output and input will be in phase, so it will go to 0 degrees. So at omega equal to omega naught, there will be a sudden change in the phase and it will go to 0 degrees. So this will be the phase response of so this will be phi of omega of this high pass function. Okay, again here there is a sudden change in the phase, and I mean instead of a graceful change, here we have a sudden change in the phase of this the high pass function. Okay, so now that we have drawn the frequency response, we'll try to analyze the time domain responses by feeding an impulse and a step to this system. So the impulse response, I'm going to split this function as 1 minus 1 by 1 plus s by omega naught the whole square. Okay, so from this I have h infinity minus h infinity into omega naught square by s square plus omega naught square. So I have fed an impulse to the system, I'm just splitting this function itself. Now if I take inverse Laplace transform of this, I'm going to get h infinity into delta of t minus h infinity omega naught sine omega naught t. Okay, so this is the transfer function I'm going to, this is the output, the impulse response h of t for an input delta of t. Okay, so now if you observe this function, there is an impulse at the output as well. There is an impulse at the output, at the output of this high pass system as well, and that again should look intuitive, because the high frequency gain of the system is infinite, h infinity, which is constant. So the instant you fed an impulse to the system, you are going to get an impulse as well at the output at t instantly at t equal to 0, because it's a high frequency input. Suddenly you are feeding an impulse with an amplitude h infinity. Okay, if the input amplitude is 1, you are going to get a gain of h infinity, and after that you'll also have a sinusoidal response after that. So if I try to plot this is going to be a sine wave which will go negative first and then go on like this. Okay, so this will be the impulse response for a high pass system. Okay, now we'll feed in a step input u of t and see what will be the response for this. So when I feed a step input, the system is actually h infinity into s by omega naught the whole square by 1 plus s by omega naught the whole square. Now for this system, when I feed 1 by s as an input, I'm going to multiply by 1 by s, so you'll be left with h infinity into s by omega naught square by 1 plus s by omega naught the whole square. So the s and s cancels out, so that's why you have s here, and this function I can rewrite it as s by s square plus omega naught square. Now if I take the inverse transform for this, I'm going to get h infinity into cos omega naught t into u of t. Okay, this function I'm actually feeding a step input with an amplitude 1. Okay, and as we can see here that this function is actually a pure sinusoid with 0 average value. So which means even though a step function has a finite average value of 1, it's a high pass filter, so it should reject the DC signal. And because it's a high pass filter, so the high frequency gain is finite, it is h infinity. The instant you apply the step input, it's going to multiply it with the high frequency gain h infinity, and you're going to get that output at the output. And after that, eventually this average value is 0. So it has to be an oscillatory behavior with 0 average value. So that's why it starts at h infinity and then goes off as a sinusoid. Okay. So again, we can also look at it intuitively. So for example, when I feed a step input, what one should expect is that you should actually, for a low pass system, you will expect eventually the output reaching the steady state value, which is h of 0 into 1. But since it's a high pass system, the steady state value should be 0, because the steady state step input doesn't have any high frequency variations. It's going to be a constant, and in the steady state this function should try to approach 0. So first, the instant you apply the input, it's going to go to h infinity, a finite value, but it will try to reach 0. The system will try to reach 0, but in the process what happens is that the energies will start getting stored in the lossless elements, either in capacitor or inductor, and they will keep switching back and forth between them, and that's how you get the sinusoidal oscillations. Okay, and mathematically, of course, we have derived a mathematical result now. I was just trying to give an intuitive explanation for it. Okay. So the third transfer function is what we call the band pass transfer function, so which is something of this type. Okay. So now for you to get a band pass transfer function, what you need is that you need the function to actually have a gain, DC gain, I mean 0 gain at DC and 0 gain at infinite frequencies. Okay. Now if you look at this function, it has a very interesting behavior for low frequencies. When omega much less than omega naught, I can ignore this term. This will be much less than 1, so I can ignore it, and the function simply reduces to s upon omega naught. Now for frequencies much greater than omega naught, okay, for omega much greater than omega naught, you can ignore again this term. The second term here in the denominator will actually be much greater than 1, and therefore I can ignore 1, and the function will reduce to omega naught by s. So for low frequencies it behaves like a differentiator, and for high frequencies it behaves like an integrator. Again, both a differentiator will have 0 gain at DC, and an integrator will have 0 gain at infinite frequencies. So therefore I meet these conditions. Okay, so it starts off as a differentiator, somewhere it transitions into an integrator. Okay, and that point where it transitions will be your the resonant frequency omega naught. Okay, so now we'll try to draw the frequency response of this function, so which is s by omega naught by 1 plus s by omega naught the whole square. So if I substitute s equals j omega, I'd get j omega by omega naught by 1 minus omega by omega naught the whole square. Now this function, we'll first plot the magnitude response. Magnitude response will simply be omega by omega naught, the j would go away, mod of this, and 1 minus omega by omega naught the whole square, again modulus of this. For low frequencies, it's going to increase linearly with a slope of 20 decibels per decade, because it's like a simple system with 0 DC or a differentiator. Okay, at the resonant frequency at omega equal to omega naught, it's going to reach infinity, and after that we discussed it's going to roll off as a first order system, first order high low pass system. So that will again have a minus 20 decibels per decade slope. Okay, the slope will be very different when you approach the omega naught. There, when you are approaching omega naught, the slope of rise and fall, I have not discussed that explicitly, but I think we will we will actually discuss how will the slope change once we go towards omega naught in a later lecture. Okay, here we can just see that I am just trying to tell you the low frequency and the high frequency behavior. At low frequencies it will rise with the slope of plus 20 dB. At high frequencies it will fall off, the gain would start falling off with a slope of minus 20 decibels per decade. Now what happens to the phase response? Okay, for the phase response, to begin with, for any omega less than omega naught, you are going to get a complex purely imaginary number, j omega naught by 1 minus omega by omega naught, this term apart from j is always going to be greater than 0. So into when I multiply it by j, you are going to get plus pi by 2. The phase is going to be plus pi by 2. And after omega naught, for omega greater than omega, any value of omega slightly greater than omega naught, you are going to get minus j omega by omega naught by, since omega by omega naught is greater than 1, I can write it this way. This term is now going to be greater than 0, and you will have a minus j here. So your phase shift will become minus pi by 2. So there will be a sudden transition of 180 degrees of phase shift. There will be a sudden transition in the phase response at the resonant frequency, and that phase shift will actually be 180 degrees. Okay, so that should again make sense, because the function is trying to become a differentiator to an integrator. Suddenly the transition happens suddenly. For a differentiator, the phase shift will be plus pi by 2. For an integrator, it is minus pi by 2, and the transition takes place at omega equal to omega naught. Okay, that's how you get the band pass response. Now we will try to derive the impulse and step response for this. This is the time domain, in time domain. So the transfer function is s by omega naught by 1 plus s by omega naught the whole square. Okay. Now for this, if I feed an impulse, I can simply write this as s omega naught by s square plus omega naught square. So if I take the inverse Laplace transform, I am going to get omega naught cos of omega naught t into u of t. So that will be your impulse response. If I feed an impulse, the response to an impulse is going to be a sinusoidal function. Okay. Again, one might ask, does this output make sense? I mean, does it have any intuitive explanations? Yes, there is. For very high frequencies, I said this system behaves like an integrator with omega naught by s. So if I feed an impulse input to an integrator, I should get a step output. Okay, so if let's say it were a pure integrator, if I fed an impulse, a delta of t as an input to the system, you would actually get an output of omega naught into u of t. But now, since it's actually not a pure integrator, okay, it would have stayed as a step input had it been a pure integrator, but it's not a pure integrator. So, but at t equal to 0, that is at very high frequencies, sudden changes, it is going to behave like an integrator. So there will be a sudden change in the output from 0 till to omega naught into u of t, and that you can see here. This is a cosine function. So the actual response it starts as a step input, but then a step output, but then it goes off as a sinusoid. Now we will feed an impulse, step function u of t, and see what kind of an output we get. So when you feed an impulse step input, so again the transfer function is s by omega naught by 1 plus s by omega naught the whole square. The step input is 1 by s. So when I feed it to this, we are going to have omega naught by s square plus omega naught as the output, omega naught square as the output. Okay, I've just multiplied 1 by s with this, and I get this. So when I take the inverse Laplace transform, I will be getting omega naught sine omega naught t into u of t. Okay. Again, this input should also look very intuitive, because a sine of x for very low frequencies, for very small at t equal to 0, okay, it's at t tending to 0, this function reduces to omega naught square into t into u of t. So it should behave like a ramp function at t equal to 0. Again, that makes sense, because it's going to behave like an integrator. Okay, so this function here is actually going to behave there is no omega naught here. This function will reduce to omega naught t into u of t. So it is just sine omega naught t into u of t. That's the step response for the system. Okay, so you are going to get a sinusoidal output. So as I said, we can look at it in very different ways. I mean, this is first, one of the ways is to look at it as an integrating system at high frequencies. Okay, and so if I feed a step input, that is 1 by s, or a step input to the system, and the system is going to behave like an integrator of value omega naught by s. So if I integrate a step, I should get a ramp input at t equal to 0, and the slope of the ramp will be omega naught, so which is what we get here as well. Okay, so if I feed step to a system like this, omega naught by s, I am going to get the output as omega naught t into u of t, and the slope of this is going to be omega naught. And also you can see that a step input in frequency domain has some finite energy at omega naught. Okay, so therefore that gets amplified by the resonant system's gain, which is infinity. So therefore you are going to get a power signal at the output. And again, the intuitions we discussed very briefly in the last lectures. Okay, so next is the final transfer function, which is a system with a 0, a complex 0, and 2 complex poles. So this is more of a very generic first order system, second order lossless system. Okay, now this system, first we will try to plot the frequency response. Okay, so again, like we discussed the same system in a first order system. So we have two cases here. First, your 0 being greater than the complex pole or the resonant frequency, and the second case, your 0 less than the resonant frequency. There are two possible cases in this example. I'm also going to call the high frequency gain h of infinity as h of 0. So for example, at very high frequencies, when omega is much greater than both omega z and omega naught, you can ignore both the ones in the numerator and denominator, and the function will simply reduce to h of 0 into omega naught by omega z the whole square. I'm going to call this as the infinite frequency gain or the high frequency gain, h infinity. So if I try to plot this response, both magnitude and phase, so first we will plot the magnitude. So the first case is when omega z is less than omega naught. Okay, I'm going to assume omega z is less than omega naught. So first you will start off at omega h of 0. So h of 0. Okay. Now at omega equal to omega z, the transfer function actually touches 0. It actually becomes 0. So for a first order system, when we discussed about first order poles and first order zeros, the transfer function really doesn't become 0 at those frequencies. Okay, because it turns, when you substitute s equal to j omega, you would get omega as a complex number. But here, for a real frequency, you are going to get a 0. So which means if I feed a sinusoid of that frequency omega z to this system, you will get 0 output of the out of the system. Okay, and similarly, if I feed a sinusoid of an input omega naught, you are going to get an infinite gain. The sinusoid is going to be amplified, which we already discussed in the last lecture. And how does it come about? Okay, so first here you are going to get a 0 here at omega z. So the function starts off at h of 0, and then it becomes 0 at omega z, and then after omega z the function will start increasing. Okay, now again at omega equal to omega naught, the function is going to blow up to infinity, and it's again going to roll off after that. I'm sorry, this is not going to roll off. So at omega equal to omega naught, the function is going to blow up to infinity. After that, at higher frequencies, we are going to get a constant value, and this value is h infinity. Okay, which I've defined h infinity here. Now we look at the phase response for this transfer function. For the phase response, since 0 comes first here, for omega less than omega z, the phase is 0 degrees anyways. The phase is 0 degrees. The instant you hit omega z, and for any omega greater than omega z, the numerator is going to become negative, right? The transfer function here, this term is going to become less than 0. So your phase will become negative. So it will go to minus 180 degrees. And it will continue to be at the same value till we hit omega naught. The moment you hit omega naught, after that, both the numerator and denominator will be negative, so you will be having a positive transfer function which will be in phase with the, both input and output will be in phase. So you will go back to 0 degrees. So for a small band of frequencies which is between omega z and omega naught, you are going to have a phase shift of 180 degrees, and for any other frequency it's going to be 0. Okay, so that's the transfer function for the frequency response of this function. And we can also draw for a similar case when omega naught is greater than omega z. When omega z is greater than omega naught. So in that case, again you start off at h of 0. So first you will be encountering omega z. So this will look like a low pass transfer function initially. Okay. After that, the function would start rolling off and it would hit the this is first you are going to hit omega naught, and then we'll get a 0, and after that the function would reach a constant value in the steady state. Okay. We have drawn for the case when omega naught is greater here. So h infinity will be greater than h of 0. I just wanted to point that out. For this case, if your omega naught is greater than omega z, omega naught occurs later, h infinity will be greater than h of 0. And similarly, for this circuit, h infinity will be less than h infinity, which is actually omega naught upon omega z, the whole square into h of 0. This will be actually less than h of 0. Okay, so this is h infinity. And the phase response, again it will be 0 initially, and at omega z it will reach minus 180, and after that it will remain constant at minus 180, and when the moment it hits omega 0, again it's going to go back to 0 degrees. So you'll have a range of frequencies for which your phase response will be minus 180. Phase response really doesn't change. Between omega naught and omega z, it's going to be 180 degrees. Okay. So that's about the frequency response of this transfer function. Now we will analyze the step and impulse response. So this function is h of 0 into 1 by 1 plus s by omega z the whole square plus 1 by s by omega naught the whole square. Okay. Now if I actually feed an impulse to this function, I can write this as h of 0 by 1 plus s by omega naught the whole square plus h of infinity into s by omega naught the whole square plus 1 plus s by omega naught the whole square. So I have written it as a low pass function and a high pass function. So this is a high pass function and a low pass function as a sum of with different DC and high frequency gains. Okay. Again, we have defined what h infinity is. H infinity is, we can simply reduce it in this way, h of 0 into omega naught by omega z the whole square. Okay, this function we can very easily reduce it to this format. So if I feed an impulse to this system, okay, I can in fact further reduce this system. I think I'll do that. So this function can also be written as h infinity into 1 minus 1 by s by omega naught the whole square. So from this I can rewrite it as h infinity plus h of 0 minus h of infinity into 1 plus s by omega naught the whole square. So this is other way of writing this function. Now if I feed an impulse to this system, okay, the Laplace transform of impulse is 1 So if I feed an impulse to the system, I just have to take inverse Laplace transform of this function. So you are going to get h infinity into delta of t plus h of 0 minus h infinity into omega naught sine omega naught t into u of t. Okay, again this function can be rearranged and you get this expression, the inverse Laplace transform. Okay, so the moment you feed an impulse, you are going to get an impulse at the output, but the amplitude is h infinity, and then depending on h of 0 greater than omega, h infinity, or h of 0 less than h infinity, you would have a sinusoid either going this way. Okay, it depends upon the magnitude of h of 0 minus, the value of h of 0 and h of infinity. So here in this case I've assumed it is h infinity is greater than h of 0. Otherwise it would be a sinusoid if h of 0 is greater than h infinity. Okay, so in that case it would be a response going in the other direction. It will be a sine wave starting here and going like this. Okay, so that's the impulse response for this function. Now similarly, the expression that I've derived here for any generic transfer functions, again in the next lecture we will start deriving those transfer functions for some standard LC circuits, and we can correlate the results. Okay, so now we'll feed a step input to this system. So this system, I'll use this expression, which is h of infinity plus h of 0 minus h of infinity by 1 plus s by omega naught square. So if I feed a step input to this system, I'm going to get the first term, you will get h of s by s, so you are going to get h infinity into u of t plus, so this is actually a low pass a transfer function. Okay, so with a, if I feed a step input with actually a gain of the low pass transfer function, you should actually get h of 0 minus h infinity. Okay, we have already showed this result. We have already shown this result. If I feed a step input to a low pass system, we'll actually get 1 minus cos omega naught t into u of t. Again, you can verify the result if you go a few moments back and see this result. Okay, so this I'm going to rearrange and write it as h of 0 into u of t plus h infinity. Okay, yeah, the steady state value is going to be h of 0 into u of t, okay, plus h of 0, I'll write it as minus h of 0 minus h of infinity into cos omega naught t. Okay, so first you can actually draw h of 0. Okay, the instant you apply a step input, what is going to happen is that we can actually writing the output in this format, it sounds more intuitive. You are going to get h of infinity. Here I'll assume h of infinity is less than h of 0. It's easier to draw it that way. Your output is going to start off as h of infinity, and then you're going to have an oscillation around that. Okay, the output is going to oscillate around that like this. So if you look at this value, the difference between these two, okay, so this value here is h of 0, okay, and the value here is h of infinity. This value, it's nothing but the difference, which is h of 0 minus h of infinity. Okay, and since it starts here, you can actually multiply this by a cos. I've just represented this signal here. Okay, and you're going to eventually it's going to reach an average value of h of 0 into u of t, but it's going to be a sinusoid with a peak to peak value. Again, it's going to go to a peak value of the difference between these two will again be okay the same as this. So the difference is going to be h of 0 minus h of infinity. Okay, so it's twice, the peak to peak value is going to be twice of this. So you can see the steady state value is going to be h of 0. Okay, the steady state value, this is going to be h of 0 into u of t, but there will also be a sinusoidal oscillatory component. Okay, in a low pass system h infinity is 0, so it directly starts off at 0, but since it's a system with a finite a second order 0, a complex 0, it's going to start off at a higher value. It's not going to start at 0, it's going to start up at a higher value, and then it will keep oscillating around h of 0. Okay, eventually the DC gain of the system is h of 0. You have fed a step input, so it should eventually reach h of 0 into u of t. This is the value it will eventually reach, but as I said, it's a lossless second order system, so there will be some oscillatory component. Okay, and again, when we take a problem and discuss it, this would become very clear. I think we'll discuss a few more problems in the next lecture. So I'll stop at this point. We have analyzed the impulse and step responses. We have also plotted the frequency responses of some generic second order lossless transfer functions. Okay, so in the next lecture I'll take some practical LC circuits, and we'll try to derive, we'll probably get almost all the transfer functions that we discussed in this lecture, and we'll try to draw the time domain response using intuitions. So I just wanted to have one place where you get all the standard results for lossless second order systems. Okay, I'll stop at this point.